What if a vector space could be split into parts that stays stable under a transformation? That's the idea behind invariant direct sums. For high-dimensional vector spaces, calculating the effect of a linear transformation becomes a significant computational burden. The interactions between dimensions create a complexity that is difficult to track simultaneously. Rather than relying on raw calculation, mathematicians at the Massachusetts Institute of Technology and other institutions sought structural clarity. They looked for ways to bypass the exhaustive processing of large matrices by identifying their internal organization. The strategy is to move away from the global transformation and instead identify specific regions of the space that can be analyzed in isolation. This is the concept of decomposition. It allows us to dissect a complex linear operator by finding the specific lines where the space naturally separates. Mastering this architectural breakdown provides the structural foundation for the canonical forms used throughout advanced linear algebra. We begin with the direct sum, partitioning a parent space V into independent subcomponents, W1 through Wk. Here, every vector has a unique representation, formed by exactly one set of component vectors drawn from these specific subspaces. To understand how an operator T interacts with these regions, we define an invariant subspace. Invariance means applying operator T to a vector inside subspace Wi traps the result within Wi's boundaries. An invariant direct sum partitions the entire space into stable regions. As T acts globally, vectors strictly stay within their respective zones. This creates a complete partition. No mathematical information crosses the boundaries between these subspaces during a transformation. Because the behavior is isolated, we can define a restriction operator, Ti. This is the operator T, acting exclusively on the smaller Wi subspace. By fusing these concepts, we replace a high-dimensional system with a series of smaller, independent, and more manageable components. While the geometric idea of isolated spaces is clear, operator theory requires an algebraic mechanism to verify this behavior. This verification relies on the principles of invariant subspaces from section 6.4 and the properties of direct sums detailed in section 6.6 of the text. We use the projection operator, EI, to map any vector in the space down onto a specific subspace, Wi. Theorem 10 states that a direct sum is invariant under T if and only if T commutes with every projection operator defining that space. The algebraic condition is simple. T times EI must equal EI times T. On the left side, TEI represents projecting a vector into the subspace first, then applying the transformation. On the right side, EIT represents transforming the vector in the open space first, then projecting the result into the subspace. Commutativity means both paths lead to the same geometric coordinate. Theorem 10 provides the precise algebraic test for geometric stability. It allows us to verify invariant structures using only operator equations. When we translate these abstract operators into a matrix, the invariant direct sum creates a highly specific physical layout. By selecting a basis for each invariant subspace and combining them into an ordered set for the whole space, the resulting matrix becomes block diagonal. This is the structure shown in equation 614. Square blocks A1 through AK run diagonally from top left to bottom right. Outside of these diagonal blocks, the rest of the matrix is empty. Specifically, these regions consist entirely of zeros. These zeros represent the absence of interaction between subspaces. They ensure that vectors in one subspace cannot influence vectors in another during the transformation. We can analyze each diagonal block AI as its own independent system. Each block is the matrix representation of the restriction operator, Ti, acting on that specific subspace. Block diagonal matrices serve as the computational evidence of an invariant direct sum, showing that the global operator has been successfully partitioned. What happens to this architecture when the subspaces can no longer be decomposed, when every block is reduced to its simplest form? Theorem 11 defines this state. A diagonalizable operator is a specialized invariant direct sum, where every subspace is a one-dimensional eigenspace. In this form, T is expressed as the sum of its distinct eigenvalues, Ci, multiplied by their corresponding projection operators, Ei. Each projection operator EI isolates the component of a vector that lies within a specific eigenspace. Once that component is isolated, the operator simply scales it by the scalar eigenvalue. For this expansion to be valid, the sum of all projections must equal the identity matrix, meaning the entire space is accounted for. Additionally, the projections must be mutually orthogonal. Multiplying any two distinct projections must yield 0. Diagonalization represents the point where an operator's action is fully resolved into a set of independent one-dimensional scaling actions. Stripped of the equations, we can see the core architectural shift. An invariant direct sum allows us to decompose complex vector spaces into stable, independent subspaces. Geometrically, it ensures behavior is isolated. Algebraically, it establishes the link between transformations and projection maps. This structural breakdown is the necessary step for building block diagonal matrices and achieving full diagonalization. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra.